Okay. Now these are the relations. So the random process, the best example of the random process is a noise voltage, right? Now noise voltage is continuously varying with respect to time. Therefore, the noise voltage is an example of the random process. So what is a noise? What is the meaning of noise? Any unwanted signal, causing interference, to the required signal, is called as noise, right? Now, any unwanted signal which is disturb the original signal is called as noise. Now there are two types of noise. One is external noise and another one is internal noise. The name itself, now this is external noise, the noise which is outside the system, the noise which is generated outside of the communication system, is called as external noise. Sir, what are the different kinds of external noises? Now this is solar noise, cosmic noise, industrial noise, atmospheric noise, see here, when that signal is transmitting out from the communication system, let us take transmitter output is a free space channel. So the signal is traveling through the channel, communication channel or transmission medium is free space. Now that signal is affected by a noise which is outside the system is called as external noise. Now one of the external noise is atmospheric noise. What is atmospheric noise? Now whenever a heavy rain or heavy storm or lightnings, if you observed or not, such kind of situations, whether it is lightnings or heavy storms or heavy rain, now under such situations you may observe that your call will not be connected even when your call is connected and a very disturbance is there. Okay, now that noise is called as atmospheric noise. This is due to lightning, or storms, rain, heavy rainfalls. Now under this situation your signals get disturbed due to the atmospheric effect. Therefore this is called as atmospheric noise and your wanted signal is get distorted. Okay, now this is called as atmospheric noise. And this is a solar noise. This is due to radiation of sun, due to the radiation of the sun rays, and this is over a shortest interval of time, but anyway, this is due to also external. And this is a cosmic noise. Now this noise is due to radiations of mainly stars and other planets, stars. And this is industrial noise. This is due to industry because of manufacturing of an electrical appliances. Now due to that particular industry, and it will create some disturbance, and which is causing disturb to our original signal, is called as industrial noise. But all these noise which are generated outside the communication system is called as external noise. But all these noise are not continuous. All these noise are over a shortest period. Am I not? How long as long as the heavy rainfall. Now at that particular period some disturbance is there, and after that it will be clear. Now at that particular storm, a few minutes or few seconds, there is a disturbance. Only a few seconds of lightning, there is a disturbance. Therefore, now this is due to a noise, but this noise is over a shortest interval, over a short period of time. So the noise which is over a short period of time is not that much affected our original signal. Okay, the noise which is continuously affected the signal is important for us. The noise over a shortest period of time is not a matter for us. Okay, now this is the noise which is generated outside the system, is called as external noise. Now we'll see what about the internal noise. Okay, now first you note on this. So this is not the dangerous noise, because that is over a only short period. Okay, now this is the dangerous noise, the noise which is generated, noise which is generated within the communication system, within the communication system. The noise which is generated within the communication system is called as internal noise. And the most predominated noise, which is nothing but the internal noise, the most dominated noise in the communication system is internal noise, because the noise which is generated within the communication system is nothing but, means what? The communication system is made up of transmitter, channel, receiver. But if you observe the transmitter and channel, observe the transmitter and receiver, all the transmitters and receivers are the electronic components, is a combination of electronic components: antenna, transducer, modulator, demodulator, and transmitting antenna, receiving antenna, oscillators, amplifiers, right? All these are the combinations of electronic components. And you know that the communication system, transmitter and receivers, are the combinations of electronic systems: resistors, capacitors, inductors, diodes, transistors, operational amplifiers. Am I right or not? ICs, all these things. But you know that all these components are sensitive to temperature. Is it right? Are sensitive to temperature? Because you know that when the temperature changes, resistance changes, because a positive temperature coefficients, all the semiconductor devices are having a temperature quotient of negative temperature quotient, right? As the temperature changes, resistance is also changes. When the resistance changes, currents also changes. But this is not the original information. This is because of the temperature changes, your original currents or original signals are gets disturbed due to variations of due to variations of temperature. You cannot avoid this. Even you are taking a cooling mechanism and all these things, which you can limit that particular, okay? So you cannot continue, you cannot extend that temperature to the cutoff range, okay? So but this temperature is definitely generated, because whenever the resistance parameters are changes, now currents are also changes. When the currents are passing through these elements, it is generates the temperatures. Now due to that temperature, our original signal is continuously affecting of somewhat. Now that effect is called as a noise. Now this is a internal noise. So therefore we can say that due to variation of temperature, this noise is because of this noise is due to variations. This noise is due to variations in the temperature. This noise is due to variations in the temperature. So internal noise. So internal noise is also called as thermal noise. Which noise? Thermal noise. So therefore, now what is the dominated noise in the communication system? The dominated noise in the communication system is nothing but thermal noise. Okay, is nothing but the thermal noise. The thermal noise which is continuously affecting the communication system, where the communication system is working. Now there definitely one noise is internally generated. Now that is called as a thermal noise, because this is due to the mainly temperature variations. Okay, so we have to have a shape of the thermal noise. What is the properties of thermal noise? Now what is the shape or a mathematical behavior of the thermal noise? Now we want to go to see. Okay, now we will see the properties of thermal noise or properties of internal noise, which is very, very important. Now this is the first properties of the thermal noise. Probability density function of thermal noise is Gaussian distribution. The probability density function of thermal noise is Gaussian distribution with zero mean. What is this? The probability density function of thermal noise is Gaussian distribution, fx of x which is equal to 1 by square root of 2 pi sigma x square into e power minus x minus mx whole square by 2 sigma x square. But this is the probability density function of Gaussian noise with mean and variance. But what is the probability density function of thermal noise? Now that's why I can write like this. The probability density function of thermal noise is Gaussian distribution, but with mean is 0. Therefore, e power minus x square by 2 sigma x square. Now this is a Gaussian distribution with mean of thermal noise is 0, and this is variance of thermal noise. Sigma n square is variance, therefore I can write like this. This is noise sigma n square e power minus, this is noise signal, and this is a variance of thermal noise. This is the probability density function of noise, thermal noise, which is Gaussian distribution, which is centered about a mean, centered about origin, because the centered value is called as mean, and variance is sigma n square. Okay, this is the first property of the thermal noise, which is Gaussian distribution with 0 mean and sigma n square as a variance. This you know that, okay? That's why we studied that distributions, Gaussian distributions, all these things. Understand or not? Now, the second one, power spectral density of thermal noise is, now let us see here. What is the noise power? The noise power, which is equal to K into Tn into B. K is Boltzmann constant, Tn is noise temperature, B is bandwidth. This is noise power. So can I write like this? K into Tn, which we call it as a noise, which is power spectral density of thermal noise. Units are watts per hertz. Sir, how can you say like this? Yes, I can say like this. K into Tn. What is K into Tn? Which is nothing but Pn by B. K into Tn is nothing but Pn by B. What is Pn? Power, watts. P. What is B? Bandwidth, hertz. Power over a frequency range is called as power spectral density. I am represented as N0, power spectral density of thermal noise. Okay. So now you see here. Now this is the power spectral density of a thermal noise, which is N0. Is it right or not? Now see here. Now the power spectral density of thermal noise, which is N0, power over a frequency range, which is N0, which is constant and which is independent of the frequency. At any two frequencies, the power spectral density is uniform, or can I say like this? Now this is N0 by 2. So can I write like this? This is one-sided power spectral density, and this is two-sided power spectral density. One-sided power spectral density and this is two-sided power spectral density. Now one-sided power spectral density which is uniform for all the frequencies, two-sided power spectral density which is uniform, which is independent of all the frequencies. Therefore, what we can say, the power spectral density of thermal noise is uniform. Power spectral density of thermal noise is uniform for all the frequencies, from minus infinity to plus infinity. This is the power spectral density of thermal noise, which is, this is, if it is one-sided you can write like this, if it is two-sided you can take like this. Okay, this is the power spectral density of thermal noise which is uniform, which is constant, which is independent of all the frequencies. All frequencies are equally distributed. Now the power spectral density is distributed at any two frequencies. For all the frequencies, the power spectral density is constant, which is equally distributed. Clear or not? Now, therefore, now see here. Thermal noise is also called, as white noise, because white color consisting of all frequencies, white light, white color, white light means what? A white color, white light, which means all frequencies, all are equally distributed, all frequencies are equally distributed. Therefore, a thermal noise is also called as white noise. The thermal noise is also called as a white noise. White means all are equally distributed, all are uniformly distributed. Okay, a thermal noise is also called as white noise. White means all colors, all are equally distributed, all are equally all colors are available here. Therefore, the power spectral density of thermal noise is also uniform for all frequencies, Therefore, thermal noise is also called as white noise. White means all are equally distributed. Therefore, power spectral density is also uniform. While comparing these two statements, now the thermal noise is called as white noise. Okay, no doubt. And another property of thermal noise is thermal noise is always additive in nature. Thermal noise is always additive in nature. Thermal noise is always additive. Addition means what we are saying. This thermal noise is called as internal noise, where the communication equipments are working, where the signal is traveling in the communication system. Definitely, along with that, noise is also traveling, because when the components are working, temperature changes, noise is generated. Therefore, the thermal noise is always additive in nature. Where there is a signal, immediately the noise is coming and added to the signal. Always additive in nature. Understand or not? Always additive in nature. So, can I say like this? That is the reason why thermal noise, internal noise, is called as additive, white, Gaussian or uniform, both are same. Additive, white, Gaussian noise is called as thermal noise. Therefore, by observing these points, we can say that thermal noise is called as, therefore, the thermal noise is called as additive, because the noise behavior is always additive in nature. White. White because whose power spectral density is uniform. Gaussian because whose probability density function is Gaussian distribution with zero mean. And finally, this is the noise. Therefore, now the thermal noise is nothing but additive white Gaussian noise. In the examination, if it is one-sided, you can take it N0. If it is two-sided, you can take N0 by 2. Therefore, now you tell me, then we have one important relation here. Now I just change all these properties for additive white Gaussian noise. Now you tell me what happened in additive white Gaussian noise. In additive white Gaussian noise, mean is, what is mean? In additive white Gaussian noise, mean equal to 0. Therefore, this is the variance of noise is nothing but mean square of noise. Now variance of noise is nothing but mean square of a noise and autocorrelation function at origin, and variance of noise mean square value of a noise, autocorrelation function at origin of the noise, which is nothing but power spectral density of noise, which is nothing but the total noise power. Total noise power. This is the total power, which is nothing but the noise power. Therefore, what is the noise power? Area under noise power spectral density, which is equal to autocorrelation function at origin. Now finally, I will write one table here. Now let us see here what happened. Very important. Now variance of thermal noise, which is equal to mean square of thermal noise, which is equal to autocorrelation function at origin of thermal noise, which is equal to area under area under power spectral density of thermal noise. What is the area under power spectral density of thermal noise for the two-sided, which is nothing but N0 by 2, N0 by 2, which is variance, which is also called as variance, which is also called as the total power, which is also called as the total power. Or you can say like this. Now what is this? This is the power spectral density, am I not? This is the power spectral density. Now this is N0 by 2. This is the power spectral density of noise. Now its inverse Fourier transform. What is the inverse Fourier transform of power spectral density? Now the power spectral density's inverse Fourier transform is nothing but autocorrelation function, am I not? A power spectral density, if you take inverse Fourier transform of power spectral density, which is nothing but autocorrelation function. Now a power spectral density of a noise whose inverse Fourier transform is nothing but autocorrelation function of noise. What is the autocorrelation function of noise? Now you tell me what is the inverse Fourier transform of a DC signal in frequency domain, which is nothing but, tell me. Now this is a DC signal in frequency domain by the duality property. Now this is nothing but an impulse. Now this is autocorrelation function, which is nothing but N0 by 2 into delta of tau. So the inverse Fourier transform of power spectral density of a noise is nothing but autocorrelation function of thermal noise, which is nothing but an impulse at origin, which is nothing but whose value is N0 by 2. Now if you have any doubt, again you see at tau equals 0. From this you can easily identify at tau equal to 0. At tau equal to 0 is nothing but Rxx of 0, autocorrelation function at origin, which is nothing but N0 by 2, delta of 0. What is delta of 0? Delta of 0 is nothing but 1, area under the impulse function, which is equal to 1. Therefore, autocorrelation function at origin, which is nothing but now power spectral density of noise. Autocorrelation function at origin is nothing but a power spectral density of noise. Is matching or not? No. Now this is a power spectral density of thermal noise. This is autocorrelation function of thermal noise. This is the noise properties, right? And there is another properties also there. Then we'll see all the properties. N number of times these are the objective questions in different competitive examination as well as the gate examinations. Now see here, autocorrelation function of thermal noise. This is the autocorrelation function of thermal noise. It depends upon the tau value or not. Autocorrelation function of thermal noise is depends upon tau value, and mean of thermal noise is constant. What is the mean of thermal noise here? The mean of thermal noise is 0, which is nothing but constant, and autocorrelation function of thermal noise is depends upon tau value. Autocorrelation function of thermal noise is depends upon tau value, and mean of thermal noise is constant. These two are valid here or not? You can check. Mean of thermal noise is 0, and autocorrelation function of thermal noise is actually n0 by 2 into delta of tau. Okay, just now we are calculating n0 by 2 into delta of tau. So autocorrelation function is depends upon tau value, right? Now as tau changes, then this will be the autocorrelation function value. If these two conditions are satisfied, and this is called as, if these two conditions are satisfied, that particular random process. Now if these two conditions are satisfied, that random process is called as wide sense stationary random process. That is called as wide sense stationary random process. Then you ask one question, sir, what is stationary random process? See, I just give one more point to you. A random variable x. Let us see here, a random variable x. If a random variable x is a function of time, is called as a random process. Now a random variable x, which is a function of time, is called as a random process. If is called as random process. A random variable x, which is a function of time, is called as random process. So random process means it should be a function of time. Now I am saying stationary random process. Stationary random process means a random process which is x of t, a random process is not a function of time. A random process is not a function of time or independent of time. Independent of time is called as stationary random process. Is called as stationary random process. Now you tell me, you keep these 3 points. If it is not a function of time, it is called as stationary random process. Yes, here mean is not a function of time. Here autocorrelation function is also not a function of time. Then these stationary random process is called as, these random process is called as stationary random process, as well as if mean is constant, as well as autocorrelation function is depends upon tau value, then that particular stationary random process is called as wide sense stationary random process. But these two are valid for what? Thermal noise. Therefore, so can we say the another property of thermal noise? The another property of thermal noise, fifth property of thermal noise, which is thermal noise is a wide sense stationary random process. Thermal noise is a wide sense noise. Thermal noise is called as wide sense noise. If any wide sense noise, that wide sense noise is nothing but the thermal noise. Wide sense noise means what? Wide sense stationary random process. Thermal noise is not a random variable, which is a random process. But that random process function of time, independent of time, is random process. A random variable is function of time is called as a random process. A random variable function of time is called as random process. But a random process is not depends upon time is called as stationary random process. In that stationary random process, autocorrelation function and mean is independent of time or a constant values, then that stationary random process is called as wide sense stationary random process. Clear or not? Which are very important for solving the problems in the noise. And this is the linear time invariant system whose impulse response is h of t, whose frequency response is h of s, filter transfer function. A linear time invariant system means transmission of thermal noise through a linear time invariant system. Transmission of noise through a linear time invariant system. Now, what should be the relation? This is a linear time invariant system whose impulse response is h of t, whose filter transfer function is h of f. Now, this is output, this is input. Now, this is the noise. This is the noise which is at the input of the linear time invariant system. Now this is the noise at the output of the linear time invariant system. So can I say this is the power spectral density of thermal noise at the input of the LTI system, which is nothing but this is power spectral density of thermal noise at the output of the linear time invariant system. Power spectral density of thermal noise at the output of the system, power spectral density of thermal noise at the input of the system. Therefore, the power spectral density of thermal noise at the output of the system, which is nothing but power spectral density of thermal noise at the input of the system multiplied with square of the filter transfer function or square of the linear time invariant system impulse response in frequency domain. You already have a proof of that. Okay. This is the power spectral density of thermal noise at the output of the filter or a system, which is nothing but power spectral density at the input of the system multiplied with the square of the frequency response of the system transfer function. So if this is the power spectral density of thermal noise at the input side is this two-sided power spectral density. Now this is the power spectral density at the output of the system, which is nothing but power spectral density at the input of the system, which is nothing but S n naught of f, which is equal to n naught by 2 into S ni of f. Okay. Therefore, noise power spectral density at the output of the system, which is nothing but noise power spectral density at the input of the system into square of the filter transfer function, which is a relation useful to study the noise analysis of analog as well as the digital systems. Now, noise is a random process and this is a wide sense stationary random process if strictly speaking. So, which we can represent mathematically with in phase and quadrature phase component. Now where you want a mathematical noise, mathematically you want a shape of a noise, so you can take this is the noise n of t with in phase with quadrature phase, in phase channel and quadrature phase, right? Now this is the in phase component and this is the quadrature phase component. Okay, so whenever you want to calculate the noise power, so expectation of n of t square, power is nothing but mean square value, which is nothing but expectation of whether it should be in phase component contributed by noise power or it may be a quadrature component which is involved for calculating the noise power. This is the noise power calculations part. You can take noise as a mathematically in time domain, mathematically represented in time domain with in phase and quadrature phase component. Okay, so this is the behavior of the noise, and with we can easily analyze the noise behavior. Now you know the shape of the noise, you know the behavior of the noise, you know the properties of the noise, you know the features of the noise, so you can see the noise behavior of analog communication system and noise behavior of a digital communication system. The noise behavior of analog communication system means we need to find the signal to noise ratios for the performance indicator of the analog system. The noise behavior of the digital communication system means a digital bits ones and zeros. Therefore, we have to calculate error probability or probability of error or error rate, which is called as error rate in the errors are in the bits. Therefore, bit error rate. Okay. The performance indicator of analog communication system is signal to noise ratio. The performance indicator of digital communication system is probability of error or bit error rate calculations in the presence of noise. Okay. So the noise means whether analog or digital, this is the noise which is a thermal noise. Okay, note down. You can easily understand the concept. Now the random signal theory problems, classroom workbook. Okay, now we'll see question number 1. Question number 1. A random communication system has a probability density function of a into e power minus b mod x. Now he is asking find cumulative distribution function, relationship between a and b Find the probability of a random variable x lies between 1 and 2. These are the questions, and he is giving one information where a equal to 3. Find the relations. Okay, not a problem. Okay. Now this is the probability density function, which is a continuous distribution, which is a uniform distribution. Okay. Now let us take first cumulative distribution function. Cumulative distribution function. Now what is the relation between cumulative distribution function and probability density function? Now the cumulative distribution function, now the probability density function, which is nothing but derivative of cumulative distribution function, and cumulative distribution function, which is nothing but integration of probability density function. Right? Now this is fx of x, cumulative distribution function, which is integration of probability density function. So can I write like this? Fx of x, which is equal to integral minus infinity to 0 a into e power, this is for negative values, mod x is minus x, plus 0 to x, positive values, mod x is plus x. So which is nothing but a by b e power bx over the limits a by b over the limits minus infinity to 0 minus a by b e power minus bx over the limits 0 to x. So this is the cumulative distribution function. Now which is nothing but a by b e power 0, which is 1, minus e power minus infinity, which is 0, minus a by b, which is e power minus bx minus e power 0 is 1. Now this is the cumulative distribution function. So the cumulative distribution function fx of x, which is equal to a by b, this is plus a by b is taken as a common, which is nothing but 2 minus e power minus bx. Right? This is the cumulative distribution function, and the second bit what he is asking is, he is asking relationship between a and b, where a equal to 3 is given. So for finding the relationship, can I find this? Area under the probability density function, which is always unity. So integration minus infinity to 0 a into e power minus b, mod x is now minus x for negative values, which is equal to integral 0 to infinity a into e power minus b, for positive values, mod x is x, which is dx, which is equal to 1. A by b e power plus bx over the limits minus infinity to 0 minus a by b e power minus bx over the limits 0 to infinity, which is equal to 1. So a by b e power 0 is 1, e power minus infinity is minus a by b e power minus infinity is 0 minus e power 0 is 1, which is equal to 1. A by b plus a by b, which is equal to 1. 2a by b, which is equal to 1. Therefore a equal to b by 2. This is the relation a equal to b by 2. Now but already a is given, a equal to 3, therefore you may take b equal to 6. This is the relation between a and b, and one more question is there, one more bit. Probability of a random variable x lies between 1 and 2. There is a relation between probability and probability density function. Now the ratio between probability and probability density function is 1 to 2 probability density function. Therefore, a probability of a random variable x lies between 1 and 2, which is nothing but integral 1 to 2 a into e power minus b mod x is for positive values of x, which is equal to x. Therefore, a by minus b into e power minus bx over the limits 1 to 2, which is nothing but probability of a random variable x lies between 1 and 2. Therefore, which is nothing but a by b, which is e power minus 2b minus e power minus b, which is nothing but e power minus b minus e power minus 2b into a by b, where b equal to, you can write 2a. A cancel. Therefore, e power minus b minus e power minus 2b by 2. This is the probability of a random variable x lies between 1 and 2.